Okay, I think we're on air now, so welcome everybody to the January 30th Rocket Club meeting. Sorry we had to move locations to online due to the icy weather here on campus. I hope the volume is working well, so this should be a live broadcast of the meeting, and I will be monitoring this Google Hangout as well as our Facebook page and YouTube as well to see if there's any comments that come in during the broadcast. So if you have any questions, fire those my way and I'll try to address them as they come in. And if I miss it, then we'll definitely answer your question at least after the fact. So let's go ahead and get started with today's topic, model rocket aerodynamics. Let's start off with some basic terminology here that we'll be throwing around throughout the presentation. So for those of you who have taken aerodynamics before, this should all be second nature or a nice refresher. If you haven't, you'll probably learn about it sometime in the next year or so when you get to that class. Or if you're just interested, these are some key terms that we'll be using today. So first one is the free stream, and when we say free stream, we're talking about everything that is, I guess, in the far field. So if we have a rocket and it's moving through the air far away from that rocket, so on the order of a meter or two, is what we're going to be calling the free stream, and the free stream direction is actually the same as the direction of motion of the rocket, not necessarily the orientation direction. We'll also be referring to the Mach number. A lot of you have heard that before. It's basically how fast you're going related to the speed of sound, and of course the speed of sound varies by temperature and by medium. Generally, that's the speed of sound is about 300 meters per second, or 1,100 feet per second, give or take, in air here on Earth during a normal temperature day. We'll also be talking about this term V infinity, the free stream velocity, so that's a speed, and M infinity, the free stream Mach number, so that's that free stream velocity divided by the speed of sound. We'll also be using rho, which is the density of air. It's about 1.2 kilograms per cubic meter on a normal day here at sea level. We'll be talking about dynamic pressure. We'll talk about that in a couple slides, actually in one slide, and what that means. Another one we'll be talking about is the drag coefficient, CD. We've got a couple different areas, the planform area and the frontal area. The planform area is basically if you took a picture of a rocket standing up on its side and you just cut out that rocket, that would be the area of that rocket cut out, whereas the frontal area is the cross-section if you're looking right down the axis. The two terms in between those, mu is the kinematic velocity and Re is the Reynolds number. We'll talk about those two later as well. The kinematic viscosity is part of the Reynolds number, so we'll mention that. And a couple of other terms that we're going to be throwing around are boundary layer, which is it's basically a thin region surrounding the body on the order of a couple of millimeters, where the flow changes its velocity and where most of the aerodynamics actually occur. And then the angle of attack is a pretty important one, and it's basically the orientation of the rocket or any vehicle that's traveling through the air with respect to the direction of motion. So let's talk about drag. When we talk about drag, we like to talk about drag coefficient because it's a non-dimensional number. It's normalized, so it describes the ratio of the force, the drag force, and the drag pressures, or the pressures that cause those forces. And when we're talking about that dynamic pressure Q, there's a formula for that. It's 1/2 rho v infinity squared. So basically 1/2 times the density of air times how fast the rocket is going squared. And this will be important later, the v squared term in there. We also have the formula for drag itself. And when you're interested in the forces on a rocket, you're interested in the drag force, not the drag coefficient. And there's a couple different ways you can describe the drag force on a rocket. It's always the dynamic pressure times the drag coefficient times a reference area. Sometimes the reference area used is that frontal cross-section area. Sometimes it's a planform area. But obviously Mother Nature doesn't discriminate, so the drag coefficients are actually based on which area reference area you're using, and it varies from place to place. Usually we'll end up using that cross-section area, the A, but in aircraft you'll usually use the planform area, S. So, what are the types of drag that we have? There's a few different types of drag. The first three are pretty fundamental and all contribute to that CD. The latter two, we'll explain that in a minute. So we have skin friction drag. Basically, you know what friction is, and so it's caused actually by the viscosity of the air. And the surface of the vehicle. There's pressure drag, which is a function of the shape of the rocket, and then there's base drag, which is very closely tied to pressure drag, but it also is influenced by the interaction of the rocket motor exhaust. Induced drag is it's a different beast. Induced drag is actually drag that is induced by lift, and most of the time we don't have rockets that have aerodynamic lift, so induced drag, it goes to 0. But if you're interested, it's a big problem with aircraft, or if your rocket has a non-zero angle of attack, you'll actually get this small induced drag term. Actually, for aircraft, it's a rather large term. And then wave drag is something that really we only care about at supersonic speeds. So let's talk about stability. I know you've heard us throw around the term CP and CG, and we've told you, oh, Open Rocket or RockSim. We usually use Open Rocket. I would say that'll calculate it for you, and it still will, and it does it fairly accurately. But if you're interested, we'll talk about a little bit about how to do that by hand, which is ultimately the driving force behind what Open Rocket does. So we talked about the center of pressure, and what it is the point through which all of your aerodynamic forces act. It's very similar to the aerodynamic center on an aircraft. Basically, if you took the distribution of pressures across the rocket, and they do change, it's the point at which you can say is the center of all those pressures acting. So if you were to only put one pressure force on the rocket, it would be there, and you'd have the same effect. Like we've told you since the beginning of whenever, it may be for you, that center of pressure should always be well behind the center of gravity, which is where all the mass, if all the mass forces were centered in one place, it'd be the CG. We say it should be one body diameter behind that CG. If you want to approximate the location of the CP, It is approximately the geometric centroid of the body. So if you're to do a paper cutout and find the average, or the point where the average area is, so to say, that's a centroid, and that's approximately where the center of pressure is. It can be more accurately predicted by something called the Barrowman equations, which we've referred to a couple of times, or just by brute force, integration, and aerodynamic methods for approximating that. So, what are these Barrowman equations? Well, there's a couple assumptions that as with all things in aerodynamics, there's all sorts of assumptions that go on. And we assume it's a relatively small angle of attack, so it's within about 10 degrees or less of the motion of the rocket. And honestly, if it's more than that, you're probably going way off track anyway. We also assume that the flight speed is lower than the speed of sound, so less than Mach 0.5. These break down at supersonic speeds, but there's other methods of predicting the center of pressure. We also assume that the flow over the body is at least moderately smooth. That's a decent assumption. It's not always the best, though. We also assume that the length to diameter ratio of the rocket, or the fineness ratio, is fairly large, which is to say that we have a rocket that is taller than it is wide, and doesn't look like a square. We also assume that there's no discontinuities in the rocket body, so everything comes to a nice point. We don't have a flat surface nose cone, or something that looks like a square. We also assume that the rocket is axially symmetric. If it's not, then we start bringing the CP to strange places. And we also assume that the fins are thin, flat plates. Similar things could be assumed with tube fins. There's ways to approximate that, but we don't assume that they're large objects that take up significant amounts of space in 3 dimensions. So the actual equations themselves, there are a lot of them, but they can be simplified without having to write them all down here, as I guess a weighted average of the CPs of the individual components to make up your rocket. So the CP of a nose cone, the CP of a body tube, the CP of the fin set. And to actually calculate those individual CPs, there's different formulas, but that approximate it. But there's this normal force coefficient, C and alpha, as you see there, that varies with geometry, and it's a coefficient, and there's all sorts of aerodynamic coefficients, and each geometry has its own coefficient, and then where the centroid of each of those objects is, we're going to call that x sub I. So basically, if you want to find the distance of the CP from, say, the tip of the nose cone, you take the summation of that normal force coefficient times the distance and divide it by the sum of the normal force coefficients. Just a little math tip, you can't cancel out the C and alphas there because it's a summation. If there's a product, you probably could, but as it is, it's not, so you have to do each of those individually, or OpenRocket does that for you. Why is stability important? I think that's pretty clear. Unstable rockets tend to spiral out of control under the slightest disturbance, and that usually leads to things not flying where they should and breaking when they shouldn't. Stable rockets, which we describe as a stability margin of 1 to 2 calibers, or the center of gravity is 1 to 2 body diameters ahead of the center of pressure, is a really good stable configuration, and any perturbation by the wind doesn't really disturb the trajectory of the rocket. So you may have a gust that blows the rocket slightly sideways, but then it aligns itself straight back into the free stream direction and continues on its trajectory. Then there's overstable rockets, where you have a stability margin greater than 2. It's not necessarily a bad thing, but you do get some interesting effects. It's basically what you have. If you look at the picture on the right, you see that normal force acting from the center of pressure, and that actually causes a moment about the center of gravity, because all rotations are going to occur about the center of gravity. So if you have a wind, the rocket is going to align itself with that wind, and actually start flying into the wind direction. And this isn't immediate, but for a sustained wind, it will eventually be directly into the wind, because it will be constantly adjusting its flight direction. But if it's a windy day, you can get significant horizontal flight, which is bad for, I guess, structural reasons, more or less. All this is pretty important because you're actually not allowed to have active control in model rocketry. So you have to do it all with fins. Let's talk about some more general aerodynamics. Aerodynamics can be broken into a handful of flight regimes. Our first flight regime that we'll talk about is the low speed regime, where we consider that air is incompressible. The density is always the same, and that goes from stationary to about Mach 0.3. This is great for little Estes rockets where you're not going very fast, but for most aviation applications and high power rocketry applications, it's generally not true. For reference, a little Cessna 172 travels below Mach 0.3, so we're talking about 100 miles per hour, a couple hundred knots, whatever, or excuse me, not a couple hundred, but just about 100 knots. That's low speed. You don't have to deal with compressibility effects. This is what AE 2020 is at Georgia Tech. The next regime that we'll talk about is the Mach 0.3 to Mach 0.7, which is compressible. It's where most commercial aircraft fly. The density of the air actually starts changing with how fast you go, and that's actually AE 3125 maybe. No, that's not right. But it's the high-speed aerodynamics class we offer. Our next flight regime is transonic, Mach 0.7 to about Mach 1.2. Some really strange things happen in there. Of course, you have the sound barrier there. So we'll talk about that too. Then there's supersonic, which is you're going faster than the speed of sound. And then hypersonic, where you're going a whole lot faster than the speed of sound, so Mach 5 and above. So let's talk about low-speed flight and how that pertains to rocketry. At low speeds, your aerodynamic forces are pretty small. Remember, you have that CD times 1/2 rho v squared times your area. Your v squared is pretty small, so your drag force is also pretty small. So light construction it's something that you can definitely do, no problem. And in fact, it's almost preferred because you don't want really heavy rockets, so you don't have to overbuild. You can use things like balsa, and that'll be just fine. So you don't have to use thick plywood or copious amounts of epoxy or any composite materials. You can also employ simple building techniques like wall mounting your fins instead of cutting a hole in the side of your rocket and mounting your fins onto the motor mount or even any part of the interior. Like I said, it really only applies to the smaller rockets because you have your small thrusts and your short flight durations don't take you to very high speeds, so you don't have to worry about the effects of high-speed flight. So, like I said, high-speed flight. You have that v squared term in there. So as your speed increases, your drag forces increase by by a square of that velocity. So for each meter per second you add, you're adding a lot more than 1 Newton of drag force. I guess as a generalization, it's maybe not quite the right numbers, but and I guess when you have a buildup in force, you have a buildup in the potential for your rocket to be ripped apart. I have interesting stories and videos of that, actually closer to the sound barrier, and not having planned for that. But in high-speed flights, you actually need heavier duty construction. As long as you're going below the speed of sound, you're usually okay with the more medium style construction of plywood fins, through wall mounting, standard fillets. Once you start getting really fast, you'll need to have reinforced structures, so maybe have some threaded rods running through your motor mount, use heavy epoxy fillets, strong materials. You can still work with cardboard, but it gets kind of dicey the faster you go. And any lack of symmetry in your design and build. So if you misalign a fin, the aerodynamic moments start adding up. So you have forces that aren't quite balanced, and those forces are getting bigger. So the moments are getting bigger. You know, go supersonic. You start getting extreme forces near that sound barrier. So you need a lot heftier construction and strong materials like phenolic, fiberglass, carbon fiber, other composite materials. Definitely avoid the really tall but really skinny rockets. Those tend to experience extremely high bending moments. So if you think about a piece of wet spaghetti, obviously it's not this bad, but that wet spaghetti tends to bend a lot, and now think of a piece of dry spaghetti. If it starts bending, it breaks, and it's bad, obviously. So I'm not recommending that you build really short, stout rockets, but definitely keep the aspect ratio there under control. The same thing really applies to the fins as well. Long, high aspect ratio fins are going to flutter a lot and shatter, which is going to you're gonna have a bad day if you do that. So next slide. Here we go. What happens to drag in compressible flows? Well, not only does the drag increase because of that v squared term, it also increases due to the fact that air is being compressed. If you think about trying to blow air into a balloon, the balloon expands, but if you have the same amount of air in that balloon and you start squeezing the box in, that air is going to change its density. You're changing the amount of mass in the same space. So the same thing kind of occurs when you have a vehicle that's flying through the air at high speeds. The air doesn't have time to get out of the way, so it all just gets compressed in together. At low speeds, it has enough time to get out of the way, and we consider air incompressible, even though it is slightly compressible. And there's an interesting rule called the Prandtl-Glauert rule. I think Prandtl and Glauert were both French guys, I believe. Don't quote me on that. But they have a really good approximation that basically states that in subsonic flows, the drag increases by a factor of 1 over the square root of 1 minus the Mach number squared. And in supersonic flow, just flip the 1 in the Mach number squared, and that describes how the drag increases with that, or as it maybe decreases. And it's important to note that this is actually the drag coefficient, not the drag force itself. So even though it looks like from the graph on the right side there that the drag forces on its way down. That's actually just the drag coefficient is on its way down, but your speed is still increasing. So you have that v squared term, and that v squared term dominates the 1 over square root of m squared minus 1. So your drag is actually still increasing, believe it or not. Now we're going to talk about some interesting phenomena that we see from aerodynamics, and the next 3 or 4 slides, I'm going to talk about various flow effects or characteristics of flows. First one we're going to talk about is laminar flow, and you'll learn about this in your aero classes. But the best way to describe it is you have streamlines that are going around a body, and basically in aerodynamics, no mass can cross a streamline. Streamlines simply move to go around objects. So air can't cross streamlines. It moves along the streamlines. And in laminar flow, all the streamlines are nice and lined up, and that boundary layer we were talking about is nice and straight. No flows going in any direction but parallel to the body. And this is the ideal flow condition. It's very low drag, or the drag coefficients in laminar conditions are very low, especially compared to the less orderly flows that we're going to be talking about in the next slide. And I throw out the Reynolds number kind of benchmark here, saying the Reynolds number is less than 500,000. You say, oh, 500,000, that's a huge number. But it's important to note that the equation for Reynolds number is a function of the speed of the flow times a reference length all over this kinematic viscosity term. And that kinematic viscosity term is usually a number that is times 10 to the negative fifth. So Reynolds numbers get really big really fast. A commercial aircraft usually flies at Reynolds. The Reynolds numbers on commercial aircraft are usually in the millions. So if that's any reference, of course, I mentioned there was a reference length. Commercial aircraft are also really big. So it's kind of a trade-off, but it basically compares the inertial forces to the fluid forces, the viscous forces on an object, and its ratio. So 500,000 actually for aerospace applications is a really low Reynolds number. What we end up seeing more often is turbulent flow, where you have Reynolds numbers over 500,000, give or take. And basically, in turbulent flow, you have very disorderly and kind of random flow in your boundary layer, which is that thin region next to the body of that's moving through air. You may look at that picture on the right and say, "Oh wow, there's nothing aerodynamic about that," and that's not entirely true. It's aerodynamic, just not very low drag aerodynamics. In fact, drag in turbulent flows is definitely higher than drag in laminar flows, just from all that disorder in there. And around modern flight vehicles, most of that flow is in fact turbulent. This isn't turbulence that you're flying through bumpy air. This is more of a local effect, just a couple millimeters in thickness. So that's kind of interesting. And obviously, sometime between the two, that flow's got to transition. So there's a region where in the boundary layer where that flow starts changing from laminar to turbulent, and you see that drag coefficient quickly rising in that region. And it's kind of a gray area around the Reynolds number of about 500,000. So it's an interesting region. Nothing particularly dangerous or exciting happens there, but it exists and it's important to note. What is kind of dangerous is flow separation, where airflow or any fluid flow is no longer following the general contour of a body, if the flow starts separating, we call this stall in aircraft. Basically, we lose all aerodynamic effectiveness. In turbulent flow, that even though it's bouncing around, the flow is still attached to the surface of the body. And in the case of the picture on the right, an airfoil. But when that flow separates, it's a harrowing situation. And you get that because of adverse pressure gradients. So basically, the pressure on the top of, or for an airfoil on top of the airfoil, is not pushing that flow down enough. And what you see is a huge spike in drag. So you lose the aerodynamic effectiveness of the surface, and you increase the drag a lot. In the case of rocketry, if you have separated flow, then the fin area behind that separated flow is no good. We speculate that this is what happened when we attempted the Club rocket with extremely long tube fins. We speculate that the flow inside those tube fins actually separated, so all of the quote-unquote fin area that we thought we had was more or less useless. This is just a speculation. We can't say for sure. There's certainly a lot of other things that played into that didn't help us, but it's a dangerous situation when you're trying to be passively stable, or in the case of an aircraft, fly through air. So just a quick review comparison. The picture on the right is actually a picture of a boundary layer, blown up quite a bit, where in all boundary layers, at the very surface of an object like the rocket body, the flow is actually stopped. It's not moving. But as you get towards the edge of the boundary layer, so a couple millimeters away, that speed has to increase in a more or less uniform kind of way. Usually it looks like a U shape. That's just kind of the way it works. And you see in laminar flows that all of those velocity vectors are parallel to each other, whereas in turbulent flow, they're kind of going here and there and everywhere. You can basically think of it as kind of an energy gradient. And when that flow runs out of energy, it starts separating from the surface. And in turbulent flows, you're exchanging all that flow energy to and from the free stream, so the air outside the rocket, to the boundary layer near the rocket. But there's that. So one thing that I'd be kind of interested to talk about is dimpling, so like a golf ball. The way dimpling works is it actually trips a boundary layer to cause the flow around the ball to become more turbulent. Yes, turbulent flow is really draggy, more so than laminar flow, but separated flows have significantly more drag than turbulent flows. So what aerodynamicists like to do is make all the flows around objects turbulent, and that's because in turbulent flows, the boundary layer is much less likely to separate than in laminar flows. So basically, we force that transition pretty soon with the dimples because it's a rough surface, so it's harder for straight parallel streamlines. and what we cause it to go turbulent immediately. This is great for golf balls because they're small objects and they travel at relatively low speeds, so their Reynolds number is actually really small. For larger vehicles, like rockets and aircraft, that flow is going to be turbulent anyway, so you don't need to be adding more, make it easier for that flow to separate by going turbulent sooner. Because eventually even turbulent flows will separate if the Reynolds number is not right. So it's really only effective at low speeds. And you can actually even see from this graph over here, if you can help it, you want that low drag as long as you want, or as long as you can before actually transitioning to the rougher surface, the turbulent flow. Actually, when I launched my level 2 up in Indiana, there was a guy there with a crown-shaped rocket that was heavily dimpled, and kind of looked at him funny and asked him why I did it, and he tried to say that dimpled surfaces were lower drag than smooth surfaces, and indeed that's the case if you're a golf ball, but there's a reason that commercial aircraft aren't dimpled all the way across. So it's really not effective. Dimpling is really not effective for most applications. So you really shouldn't go out of your way to add dimples to all of your projects. It would be an interesting thing for you to do, but I don't think it's really worth your while to do that. So let's talk about the aerodynamics of some commonplace rocket parts. We'll start with the nose cones. Nose cones, it's the first thing the air sees on your rocket, so say make a good impression. But actually, the nose cone it has a lot of effect on the drag of the rocket. There's a bunch of different nose cone shapes, as you can see from that graphic on the right-hand side. Most of the nose cones that we use in rocketry are ogives. That's basically a section of a circle cut at an interesting angle. But if you're interested in what an ogive actually is, you can read about those online. We also use a lot of conical nose cones because they're easy to make. Not quite as common as the ogives, but they do exist. I guess the minimum drag body nose cone that we have is called the von Karman ogive, or just a von Karman nose cone, and it's actually uses a very specific mathematical equation to minimize the drag for a given diameter. There's also the Sears hack body, which is similar, but it minimizes drag for a given volume. Of course, you don't see any Sears hack nose cones out there, because it's pretty much the same thing as von Karman ogive. Slightly different in the design equations, but the similar idea. Then there's other shapes as well. You see elliptical nose cones, and then there's also power series, so mathematical power series that can be used to come up with a nose cone shape. And actually, on the right-hand side, you can see how good each of those different types of nose cones are at different flight speeds. 1 being superior and 4 being inferior. Sorry that the graphic starts at Mach 0.8 and goes to Mach 2. I realize that's probably not useful for most of you. And it also makes it look like the ogive and the cone are all around inferior. That's actually not the case. The ogive is pretty good at low speeds, and actually the cone is pretty good at supersonic speeds. But that's neither here nor there. Obviously, like I said, that von Karman shape is superior. And you actually, if you want a von Karman nose cone, you pay for it quite heavily when you buy a nose cone. And so there are different shapes perform better at certain Mach regimes. So that's kind of an interesting effect there. So, what effect does the length of the rocket have on aerodynamics? Well, longer rockets, they have more surface area, so you tend to have increase in skin friction drag. So there's that. But when you increase that fineness ratio, so the ratio of the length of the rocket to the diameter, you actually have a decrease in pressure drag per unit volume. So this is not to say that there's either merits or dismerits to having a long rocket, but just some interesting stats on that. And it's interesting to note that, or I guess it's important to note that the longer rockets that you have, the really tall, skinny ones, are subject to higher bending moments. And there's some good images out there on the internet of really tall rockets that people build, kind of as a joke, kind of as a challenge, that when they fly, they are notably not straight. They've got quite a curve to them, and if you don't build that into consideration, you may end up snapping the rocket in half, and then the whole flight ruining itself. So I'm not trying to scare you away from really long rockets. Most things that you build are probably going to be completely capable of handling the moments that they're given. But if you have a 3-inch diameter rocket, don't try and build it 9 feet tall. That's you're setting yourself up for an interesting situation where you may not get that rocket back in one piece. The interesting thing that a lot of people like to ask about is fin aerodynamics. And an open rocket, you usually see that there's 3 different options for fins. There's your square cross-section, your rounded cross-section, and your airfoil cross-section. And each of those have different aerodynamic characteristics. The square, or I like to call it rectangular, because most of your cross-sections are notably not square, they're more rectangles, are usually what you're going to end up using. So that's basically taking a piece of wood and cutting out with a laser cutter, but not doing anything else to it. And those are really easy to manufacture. You don't have to profile any part of it. But it comes at the cost of having a relatively high drag coefficient for fins of similar thickness to chord ratios, the chord being the length from the tip to the trailing edge, from tip to tip. Rounded cross sections, where you're blunting the leading edge and the trailing edge, they're not too difficult to manufacture. They're still a challenge, especially if you have something like plywood that is not meant to be sanded. If you have balsa, it's usually pretty easy. And they actually have decent performance, aerodynamically, less drag, but still not the absolute best, especially when you compare it to other options that you have, like the airfoil fin. Obviously, this is kind of an optimal cross-section for rocket fins when you're going below the speed of sound, but above the speed of sound, traditional airfoil shapes are not necessarily the most aerodynamic. That's actually what the wedges are for, and that has to do with the shocks that you have. That's a topic for a whole nother meeting, though. One thing you do have to be careful with airfoil cross sections is that they're symmetric. If there's any asymmetry in that cross section, you start generating lift with the fin, which can cause something as innocent as spin, or as dangerous as actually causing the whole rocket to start pitching. So usually airfoils cross sections are a lot harder to pull off, take a whole lot of work and effort and attention to detail, but they definitely offer superior aerodynamic performance at low speeds. Wedges are kind of the airfoils of supersonic rockets. If you were to buy a rocket kit from someone like Wildman, you may find that actually the fins are sanded off to a wedge tip and a wedge trailing edge, and you get decent aerodynamic performance at subsonic speeds. Not as good as an airfoil cross section, because you're actually deflecting the air instead of having the air run straight into a brick wall, just about. But they're really good at supersonic speed. So if you look at like a F-22, you actually won't see a traditional curved airfoil like you might see on a Boeing 747. You'll see more of a wedge-shaped airfoil. That's just because of the way that shocks are deflected off of wedge shapes, and it's usually better for that. So you get oblique shocks instead of bow shocks. Oblique shocks tend to be lower drag than the bow shocks, which are actually really high drag. But that's neither here nor there for this. If you're thinking about going to supersonic speeds with a rocket, I would definitely recommend trying to wedge your airfoil or wedge your fins. That'll go long distances for you. Next thing, this is kind of more related to aircraft than anything, but the actual sweep of your fins. You may say, oh, all my fins are already swept, and that's probably mostly true. But the interesting thing that you get out of that is wing sweep or fin sweep actually reduces the effective Mach number over that surface. And if you remember the relationship between Mach number and the drag coefficient, if you can reduce that effective Mach number, you'll actually reduce that drag coefficient. And since you're traveling at the same velocity, even though that velocity may not correspond to the free stream Mach number, you'll actually decrease the overall drag, which is a pretty good thing, since you're decreasing the forces on the rocket. And it decreases it by a factor of the cosine of the sweep angle. And that sweep angle is defined as not the angle between the leading edge and a line perpendicular to the rocket. Rather, it's defined as the mean chord. So if you look right here, from here to here, this was your mean chord, so kind of the center line of the wing or the fin. That is the point from which the sweep angle is defined in aerodynamics. And of course, this is the same as the angle from the leading edge to perpendicular if and only if you have rectangular fins that kind of just come out and don't actually rejoin the base of the rocket. Most are trapezoidal, so the mean chord line is not the same as that leading edge angle. Another interesting thing that sweeping your fins does is it brings the center of pressure aftward. That's just moving that fin surface backwards. So that's a plus. Another thing I want to talk about is ballistics, and it's exactly what it sounds like. That's because that's what rocketry is. You have your ratio between your inertial forces and your drag forces. So mass times gravity. over your drag force, or we can just simplify it as saying the mass over the drag coefficient times the frontal area of the rocket. And this is interesting to study because actually in flight, drag tends to slow down large and lightweight objects a lot more quickly than it slows down heavy and dense objects. So we come up with this ballistic coefficient. So if you want a rocket to go higher, usually you want to increase that ballistic coefficient, even though that's increasing the mass. It could also be decreasing the drag or the area. And you do this because in rocketry, most of the altitude is gained on the coast phase, not the boost phase. So you gain more altitude when you're not using your motor than when you are using your motor, which may be kind of counter to intuition. The next few slides are more related to aeroelasticity and some different failure modes of your fins. So the first one, and I'd like to thank Tanzu for these slides, is kind of static failure, or we call it divergence. And this usually happens in forward swept wings and fins. And basically what you get is when you have an aerodynamic load applied to the fins or the wings, it deflects the wings, so it causes them to start pitching, or bending, or being in any direction other than just kind of flat and straight. And that actually causes an increase in the aerodynamic load, which causes more bending and more flexing. And eventually this leads to structural failure. If you sweep your fins afterward, so backwards instead of forwards, divergence isn't really an issue. And that's kind of why you see aircraft with aft swept fins rather than forward swept fins. Probably a more interesting failure mode for most people is dynamic failure. And usually what we like to talk about is fin flutter. And we say elastic fins, but all materials really are elastic. Kind of hit a resonance point, so they start vibrating, and that vibration starts amplifying itself because it's at the correct frequency. That actually causes that resonant response, and eventually you start fluttering so much that it just rips the fins off or snaps them in half, which is of course a bad thing because you no longer have that fin surface to keep you stable. This has happened in many a rocket. Then you also have a buffeting, which is kind of a high frequency vibration that causes a lot of shaking, and this happens near the sound barrier. You hear stories of a lot of the early test pilots talk about an extreme shaking when they got near the sound barrier, and this is because you have moving kind of separation, flow separation, and shock waves. Then another interesting failure mode, dynamic failure mode, is this transonic aeroelasticity, and this happens because shock waves, in the transonic regime, you have local areas where your speed over the body is supersonic and other areas where it's not. And so these supersonic features and shock waves can move abruptly and cause things to go to hell in a handbasket really quickly. Excuse me. I'd like to show a quick video of kind of a flutter failure mode. You see the wing here vibrating, and it reaches an oscillation point. And this is all from aerodynamics, and it rips itself apart. This can happen in rocketry, so I'm not trying to scare anybody, but this is an interesting phenomenon that kind of occurs when you have large aspect ratio fins made of thin materials, thin elastic materials, and are traveling at interesting flight speeds. So the last thing you kind of want to take away is the implications of aerodynamics on model rocketry, which is kind of what I was hoping to get out of everything. Obviously, the long and short of this is that aerodynamics are extremely important when we're talking about rocket performance. They're just as important as any other major subsystem on the rockets, like propulsion or structures. If you have bad aerodynamics, you're going to have bad performance. So depending on the mission you choose to pursue, to make it sound very official, the aerodynamics are an important consideration to make. They definitely drive the decisions you make about your rocket geometry and the materials you decide to use, because you have to take into account those aerodynamic forces and make sure that you're able to achieve what you want to. If you're trying to go past the speed of sound, having balsa, fins, and paper rocket is probably not going to do you much good. A lot of it's intuitive, so you don't have to do complex analysis. So basically, streamlined shapes, smooth contours, everything that you might associate with aerodynamic shapes. It's pretty intuitive. But if you're interested in the actual science of aerodynamics, there's a lot you can do with the analysis, aerodynamic analysis, and you actually learn a lot of that in the aerodynamics classes. But just a quick back of the envelope calculation can go a long way for some simple analysis for various calculations of flight. So you can calculate your stability and your ability to withstand drags and shocks, or at least your what kind of forces you're going to be seeing at various speeds. A quick calculation is saying that you're going to be going past the speed of sound might indicate that you want to have a more heftily built rocket. Or you could say if you're going to be going near the speed of sound, your center of pressure is actually going to change because of that Prandtl-Glauert rule. It doesn't apply to just drag; it actually applies to all aerodynamic forces like lift, pitching moment, and that normal force as well. So you can say that normal force coefficient is going to change with Mach number as well. So that actually concludes our presentation on model rocket aerodynamics. I hope this was informative and interesting. I'd like to thank everybody that's joined. It looks like we've gotten up to 7 viewers at once, which is pretty cool. And I believe this will also immediately be published to our YouTube account, so if you want to go back and watch it later or have a friend watch it, I think that should be posted online. And if it's not, you guys are lucky you got to see it. But I'll have these slides available if anybody's ever interested in learning more about the topic. So just like to close by saying I'll see you all next week. We'll have our meetings at our normal time in our normal place, assuming it doesn't snow. I don't think it will. So send me topics that you'd be interested in talking about, and have a good week. Stay warm and stay safe.